In our last video, we saw how to take an irreducible polynomial over a coefficient field, so it has no roots in that coefficient field, and then extend the coefficient field using a quotient construction, so that in that extended field, that polynomial does have a root. We saw a couple of examples of it in the last video. Now we're going to start by just arguing for why that always works, why that quotient construction will always give us an extended field in which that polynomial has a root. After that, we'll look at the other question, which is, let's suppose we know exactly what number we would like to throw in with our smaller field. Can we find the smallest such extended field that contains the original field as well as that new number? So first is the this always works theorem for the quotient construction that we looked at in the previous video. And it says, if f is a field and p is an irreducible polynomial over f, that's at least quadratic, so we got to do something interesting here. Then if I take the polynomial ring f adjoin t, and I take the quotient by the principal ideal generated by p, our irreducible polynomial, then the result is, first of all, always going to be a field. So again, this is the construction where we build the polynomial ring, and then we take the quotient by the principal ideal generated by p, which really just means that we're setting p and therefore all of its multiples equal to 0 in the quotient. So the first important observation is that this E, this quotient, is a field. And the reason E is a field is that P is, by presumption, an irreducible polynomial. And since f adjoin T is a principal ideal domain, that means that the ideal generated by P is a maximal ideal. And whenever we take the quotient of a commutative ring by one of its maximal ideals, we get a field. So that's the first observation, is that this is always a field, and it extends F. Why does it extend F? Because this monomorphism can locate f inside of E. All we have to do is take every element of f and send it to the coset f plus the principal ideal generated by P. So we can locate a copy of f inside of E, therefore E is an extension of f. And finally, the most important thing, the reason why we did this whole construction, is that this new field E contains a root of our polynomial P, where the original field f did not. And by construction, that element is exactly the thing that we call T, because we exactly set P of t and all of its multiples equal to 0 inside of this quotient. So this is sometimes called the fundamental theorem of field theory, because it's the construction that we can always use to give us a root where there was no root before. For example, starting with a polynomial with rational coefficients, all of whose roots are irrational, if we apply this construction, we're guaranteed to at least get one root of that polynomial inside of our extended field. So what about going the other way around? How do we introduce Q, the rational number system, to a new friend? Instead of a polynomial, we know what new irrational number that we want in our field. So let's take the cube root of 2, for example. You can convince yourself using some basic number theory that that's an irrational number, so it doesn't belong to Q. But what field does it belong to? Well, it belongs to the complex numbers, but again, that's not an interesting example for us. We would like to find somehow the simplest, the most parsimonious. We want the field which is bigger than Q, but only just big enough to contain the cube root of 2. How do we do that? What other fields does cube root of 2 belong to? Well, it also belongs to the real numbers. But the real numbers are also boring because they're way too much bigger than the rationals. So we'd really like to figure out if there is a smallest extension field E that contains the rationals and also contains the irrational number cube root of 2. So first we have to talk about the kinds of outsiders, the kinds of irrational numbers that exist out in the wild. The cube root of 2 is one kind, but there are other kinds that are even nastier to work with. So let's suppose f is a field, and alpha is an element which does not belong to f, whatever that means. It's not very interesting to say that because we haven't said where alpha belongs, but that depends on what kind of an outsider alpha is. So we're going to say that alpha is an algebraic number over f if it satisfies a polynomial equation with coefficients in f. These are going to be the most interesting examples for us because they have something to do with polynomials, and that's really what we're concerned with. And the reason that this gives us interesting algebra is when a number is algebraic over the field f, when it satisfies a polynomial equation over f, that means that we can do some arithmetic combinations to it, raise it to certain powers, multiply it by some elements of f, add and subtract those together, and the result ends up landing back in f, even if alpha itself was not. So here are some examples of algebraic numbers. The square root of 2 is algebraic over the rationals. twice the cosine of pi over 9, which is kind of an interesting example because it certainly doesn't look like this thing should be algebraic, but it turns out it is. You can show that it satisfies the equation t cubed minus 3t minus 1 is equal to 0, so that makes it algebraic over the rational numbers also. The number pi squared is it's algebraic over the real numbers. So it's important always to specify when you say algebraic over what? Pi squared is algebraic over the reals because it satisfies the polynomial equation t squared minus pi is equal to 0. And pi, if we're convinced this is a real number, that means that pi squared is algebraic over the reals. But is pi algebraic over the rationals? We know pi is irrational, but does it satisfy a polynomial equation with rational coefficients? If it does not, then we call it a transcendental number. So a number is transcendental over f if it does not satisfy any polynomial equation over f. So algebraic and transcendental take care of both possibilities. Either alpha satisfies a polynomial equation over f, or alpha does not. In the first case, it's called algebraic over f. In the second place, transcendental over f. The transcendental numbers are a little nastier. It turns out that they're also more common, at least among the real numbers. If you take all the real numbers and you put them on a dartboard and you throw a dart at that board, the chances are 100% that you're going to hit a transcendental number over the rationals. So what do I mean by that? Well, it turns out that the algebraic numbers, in other words, numbers that are algebraic over the rationals, form a countable set. But the transcendental numbers, because they're the complement of the algebraic numbers inside of the reals, the transcendental numbers are therefore an uncountable set. And so there are so many more transcendentals than there are algebraics when it comes to the real numbers, although the algebraic numbers are the ones that we're the most interested in. So what are some examples of transcendental numbers over the rationals? How about pi and e? Now, it turns out not to be a trivial thing at all to prove that pi and e are transcendental. Those proofs only came along in the 19th century. And what's perhaps even more surprising is that if we take pi and e and we combine them together in a variety of ways, even just as something as simple as adding them together and ask, is pi plus e a transcendental number? That question remains open as of the making of this video. So maybe that's something that you can look into. It's one of many unsolved problems in what's called the theory of transcendence. So how about that cube root of 2? How do I find the smallest field extension of the rationals that contains that cube root of 2? Well, let's start by building it up. So we have the rationals, and we can describe the rationals as the set of all a's such that a is a rational number. It's not very interesting. So let's take this number, cube root of 2, and let's try throwing it in with alpha. Now, what do I mean by that? What I mean by that is I'm going to take and define a new field, which consists of linear combinations of 1 and the cube root of 2, with those coefficients being rational. So a plus b times the cube root of 2. That gives me a field that's a little bit bigger than q. And again, if we send a to a plus 0 times 2 to the 1/3, that shows that there's a monomorphism from q into this field e. So now we have a slightly bigger field that contains the cube root of 2, a equals 0 and b equals 1, and it also contains all the rationals, a equals 1, b equals 0, for example. But if this e is to be a field, that means it also needs to be closed under multiplication, which means we should be able to multiply the cube root of 2 by itself, for example, and remain inside of e. So it's not enough just to include the cube root of 2. We also have to include the cube root of 2 times the cube root of 2. Another way of writing that is 2 to the 2/3, or the cube root of 4. So the cube root of 4 has to be a part of our extension as well. And therefore, every rational multiple of the cube root of 4 must also be a part of our extension. So now we're getting a little bit bigger still. But again, if this new field is supposed to be a field, it has to be closed under multiplication. And so it also must contain 2 to the 2/3 times 2 to the 1/3, or the cube root of 4 times the cube root of 2. But of course, the cube root of 4 times the cubed root of 2 is the cube root of 8, which is 2 again, and that lands back inside of our base field, the rationals. So in other words, we started with this element, cube root of 2. Its first power belonged to our new extended field. Its second power also was irrational and belonged to our extended field. But by the time we took the third power, we landed back inside of Q. And if we landed back inside of Q for the third power, that means we're also going to land back inside of our field for the fourth power. So the first power was in E, the second power was in E, the third power was back in Q. Therefore, the fourth power, which is 2 times the cube root of 2, ends up, again, back in E. So we're not getting anything interesting once we get past the second power of the cube root of 2. So it's enough for our extension field to just have the rationals, the cube root of 2, and the cube root of 4. So here's a way of looking at this from the perspective of linear algebra. This extended field, E, is a three-dimensional vector space over the rational numbers. So we can sort of visualize it as though it's XYZ space somehow. So we have one axis which contains the rational numbers on it, and then orthogonal to that somehow, we have an axis that contains all of the rational multiples of the cube root of 2 on it. And then orthogonal to each of those, we have another axis that contains all the rational multiples of the cube root of 4 on it. So here's our XYZ space, which forms our extended field E. And so any element inside of this space is going to be some rational linear combination of 1, the cube root of 2, and the cube root of 4. So here's an example of one, 23/8 plus 3 cube root of 2 plus 11/6 cube root of 4. So that belongs to E. And from a linear algebra perspective, we can say that the basis of this three-dimensional vector space consists of the numbers 1, which belongs to Q, the cube root of 2, which does not, and the cube root of 4, which does not belong to the Q either. So we have kind of this three-dimensional vector space, which forms our extended field E. And here's a this always works theorem for that example as well. That for any field F, if I have a number which is algebraic over F, and if P is a polynomial that satisfies P of alpha equals 0. So I start with an algebraic number, alpha, and then I find some polynomial of which alpha is a root. Then the theorem says that there exists a number k which is less than or equal to n, which is the degree of this polynomial, such that this set that I get by taking linear combinations of powers of alpha along with 1 all the way up to the kth power of alpha is going to be a field extension of F, and it's going to contain alpha inside of it. And here's the most important word in this whole theorem, it's going to be the smallest such extension field. So there's our parsimony requirement. So this again, just like our previous example, is going to be a vector space over F, and a basis for that vector space is going to consist first of all of 1, and the reason that we have this 1 in here is so that we can locate F, the base field, inside of E, and then we have all the powers of alpha up to alpha to the k. If all of those are independent over F, then this is a linearly independent spanning set, therefore a basis for E. And when this happens, when the this always works theorem is invoked, we call this F parentheses alpha, or F adjoin alpha. This is the smallest field that extends F and contains the number alpha inside of it. But now to finish, I want to muddy the waters just a little bit, because there is more than one way to create such an extension field. So we're going to look at how to extend the rational numbers to include the golden ratio. Because I want to do this example justice, let's make this a separate video. So in the next video, we'll look at two different ways to introduce the rational numbers to the golden ratio, 1 plus radical 5 over 2, and look at what the difference is between those two different ways.